Alrighty, so last place we stopped, so we're doing section 7.5, strategies for integration. I just talked about, all the sort of mental steps you have to go through when you're working on one of these problems. And now we're just going to do a couple examples where, it's the typical problem that you get handed when we're learning integration. You get handed an integral and asked to integrate it. You're not told how to do it. So let's just jump into example one. So there are a couple, they're just, the rest of this section is just examples. And then we will talk about whether or not, if I hand you something, you're actually able to integrate it. And we'll see some examples of why that isn't true. So anyway, so let's just jump into these examples. So we want to evaluate the integral of tan cubed x divided by cosine cubed x dx. And so, when you go through the steps, the first one is to simplify as much as possible. And, my first thing when I look at this is, I see this and I say, okay, well, tangent and cosine don't go together. Tangent and secant will go together, and cosine and sine will go together because um, those are the kinds of u substitutions we do. So when I'm doing this, I don't want to do this in terms of tangent and cosine. I want to switch one of these. I'm going to just write this as tan cubed x cosine cubed x dx. Sorry, secant cubed. Sorry, 1 over cosine is secant. Okay. So now what we're going to do is we are going to, the book stops here and it says you can use section 7.2. I'm going to do a couple of these, the easy ones at least. So what we're looking for is, I want to be able to write one of these in terms of the other, and so it might not matter. Well, yeah, it does in this case. So, you can go through the advice, but the way I do these is I look at these and try and think about what would happen. I can either separate, so I want to separate, something for a u substitution. So I can either separate a tan squared, or I can separate a tan theta or tan x secant x. When you look at this, so if you separate off a tan squared, you're going to be left with, one factor of tangent there. And that's not going to be something we want to work with. We want to work with tan squared or secant squared because we have those trig identities. So let's separate off a factor of tangent secant. So I have tan squared x secant squared x times tangent x secant of x dx. Let me clean that up. And now what we're going to do is we're going to, so right here, this is the derivative of secant, of course. So if I want to do a u substitution, I'm going to need to let my u be secant theta or secant x then. So what I want to do is I want to write everything in terms of secant. So tan squared is going to be 1 minus secant squared minus 1, sorry. Doing that in my head. And then I have a secant squared x tan x secant x dx. And now, I can see that if I let u equal secant theta or secant x, I'm used to writing thetas, but u equals secant x, du will be secant tangent dx, and that appears, right there at the end of the integral. So then I can write this. This is the integral of u squared minus 1 times u squared du. And now this integral is a lot easier. I'm just going to go ahead and write the answer in terms of u. But then we're not interested in this in terms of u. Replace u back with secant cubed x over 3 plus my constant. And again, this isn't about, doing these integrals. It's about recognizing that that this integral is of this form, and use these ideas to do it. So you can do the same thing if you want to if you want to put things in terms of sine and cosine, that's fine. Let's do another example. So the integral e to the square root of x dx. This one, there's no simplifications you can make to this. There aren't any u substitutions or so. If you try and look for a u substitution right off the bat, you're going to be left looking for, the derivative of anything there. So what we're going to do is, if we look back, so if you look back in the notes at, the strategies, 3D part 2 says to try a u substitution if we have a square root. So we're going to try u is equal to the square root of x and see where that takes us. So then du is 1 over 2 radical x dx. And so we get dx is equal to 2 radical x du. So then this is equal to then the integral e to the u, and then dx is 2 radical x du. Pull the 2 out. Problem is I don't want a square root of x in here. I want everything in terms of u. But, choosing u equals to the square root of x, that helps me out here, because the square root of x is just u. And now this integral can be done. So this is something that you can integrate by parts. So let's see. So you would let u equal, we have to choose different variables here. Let's use s and t. So s would be then u, because I want to differentiate that. dt would be e to the u. ds would be du. And t would be, e to the u du. T would be e to the u. So then we would have this is 2 times u e to the u minus the integral TDS, in this case, e to the u du, 2 u e to the u minus e to the u plus my arbitrary integration constant. Okay. So for this one, again, the point was I had, a square root and nothing else. I didn't have any obvious u substitutions, and I couldn't integrate by parts and get something useful. So the idea was, just let u equal the square root of x, see what happens, and in this case, it works. Okay. So next one. So we have the integral dx over x square root of the natural log of x. So you go through this, again, can't simplify. That doesn't work. But, you start looking for u substitution then, and this one has a u substitution. So letting u equal ln of x, I'll get a 1 over x when I differentiate. So it looks like the u substitution here is u is 1 over ln of x, u is ln of x. Du is 1 over x dx, which appears here. So, okay, so then this is then, go back to black pen, this is then the integral, so I can do it like this. So we have dx is x du, if you're still want to do it that way. So we have x du over x square root of u, since ln of x is now u. So this is the integral du over the square root of u. So this is the integral u to the minus 1/2 du. I'm going to stop it there because that's a really simple one. Just one note on this last example. You want to put everything back in terms of x, whatever, so u was square root of x. So you would just plug that back in. Forgot to do that on the last example. This example, you would integrate this, and then you would plug back in terms of x. All right, so there's one more example, and then we're going to talk about, these are really quick to go through, but so we have, so we have the integral of the square root of 1 minus x over 1 plus x dx. Okay, so this one is, kind of a tricky one. There are some, u substitutions that'll work here. What you can do instead is you can do some simplifications to this one to make it a little easier. So what we do is we take this, and remember, if I have the square root of two things divided by each other, this is square root of 1 minus x divided by the square root of 1 plus x. I can always write that. We're going to multiply by 1. When I say multiply by 1, we're going to multiply by one thing divided by itself, and we're going to try and rationalize this. So we're going to multiply, in this case, square root of 1 minus x. Dx. And so, the point of that is, I'm going to get, when I do that, the reason that's going to work, or the reason that's going to be helpful is I'm going to get, something like 1 minus x squared or something in like that in the bottom. And then it starts to look like, a trig substitution problem. So when I simplify this, let me get rid of that arrow. When I simplify this, I'm going to get, so the top is square root of 1 minus x times square root of 1 minus x. So that's square root of 1 minus x squared, or just 1 minus x, divided by the bottom is a difference of squares, 1 minus x squared. You just multiply the two polynomials on the bottom. And now I can separate this into two integrals, one divided by the square root of 1 minus x squared dx minus the integral x divided by square root 1 minus x squared dx. So the first one is, so you can just look in the table of integrals, this is arc sign. The second one you can do a u substitution for, and you would end up getting 1 minus square root of 1 minus x squared and your integration constant. So that integrates directly. This is a u sub and your integration constant. Okay, so that was one where we could simplify things and get something that we can integrate directly. So the last part of this, last part of this section, this is a faster chapter. The next one's going to be several videos. But we have this question. Can an antiderivative be found for any continuous function? So what that's saying is, can I integrate any continuous function? Can I, that's not a good way to put that, but so I'm going to leave it as, can an antiderivative be found for any continuous function? And the answer is no. So as an example, so from statistics, you have the normal distribution, right? If you're taking a statistics class, and you'll know that statistics relies heavily on calculus, because we're interested in the areas under these curves in statistics. So areas under distributions tell us probabilities. So this graph here is e to the minus x squared. So that looks like that. But if you try and if I gave you this integral, and I asked you to find an antiderivative for me because I want to be able to find this area for any bounds that I may have, you're going to come up empty. So you can sit here, you can try every technique you know, you can try every technique you don't know. You're not going to be able to write something like this down in terms of the functions we have. There is, when that happens in mathematics, what we do is we just define this to be a new function. So if you read about this, you'll end up reading about the error function, ERROR. And that's still not, the functions that we know. But the point is, even if you're handed something, there's always the possibility that, I'm not going to be able to find that integral. Obviously, we're not going to do that to you on an exam or anything, but, in real life, you are going to come across things that, have everyday applications, like the normal distribution, and, we can't really actually integrate them. And this is why, when we go through and we do Riemann sums in Calc 1. So when we make you do the rectangles um, underneath the function and add them all up, that's actually really important for things like this. So in order to be able to do statistics, you need to be able to integrate things that look like this, at least for, normally distributed variables. And so, if you want to actually be able to do that, instead of being able to just write down an integral or write down an antiderivative, and apply the fundamental theorem of calculus, you're going to have to rely on a computer. You're either going to have to write a program that will do this as a Riemann sum, or rely on some other program that already can do these Riemann sums, or has the values of the error function tabulated, but that's different. But so just keep in mind that as we're doing all these, the question of integration is a lot harder. You can't write down an antiderivative for any function that's handed to you. The last part of this book is, it gives a bunch of these that you might think, have antiderivatives. So like e to the x over x, sine of x squared won't have an antiderivative that you can write down. And there are more. You can look at them in the back of section 7.5 if you would like. So I'm going to stop this. This is the end of chapter 7. Again, if you're looking for good practice for the exam in terms of evaluating integrals, this chapter is really good for it. They just hand you a bunch of functions to integrate. They don't tell you what process to use. So that's really good practice in teaching yourself how to identify the different methods to use. So I'm going to stop